Hello everyone, this is Mrs. Lim and this will be the first video of electromagnetism. Before we start off with electromagnetism, let's go through some recap about what we have learned in the previous chapter on magnetism. Okay, so I have 4 statements over here. Read the statements and tell me which of the following statement is true. Okay, I'm going to go through the answers now. Okay, the first one where all metals are magnetic material is wrong because there are only 4 metals that are magnetic material, which is iron, cobalt, nickel, steel. Okay, and then next, all conductors are magnetic material is also wrong. For example, coppers are good conductors, but they are not magnetic materials. Next, all materials that can be electrically charged are magnetic material. This is similar to B. When they can be electrically charged, usually they are a conductor. Okay, so it's not all. Okay, and the correct answer is D. Okay, any material that can affect the direction of compass needle are magnetic materials because a compass needle is actually a magnet. So a magnet will be affected by either by any magnetic materials nearby. Okay, it can be a magnet or magnetic material. It will cause attraction and repulsion. Okay, so the answer is D. Next question. A soft magnetic material can be easily magnetized and retains its magnetism longer. The answer to this question is false because a soft magnetic material like iron, it can be easily magnetized, but it also loses its magnetism easily. It doesn't retain its magnetism. It's hard magnetic material that is hard to magnetize, but it will retain its magnetism longer. Okay, next. Okay, so we move on into electromagnetism, whereby we will study the effect of electricity combined with magnets. Okay, in the previous chapter, when you have learned about electromagnets, we have already covered a little bit about it, whereby whenever we have a current flowing through a solenoid, there will be a magnetic field around a solenoid. Okay, but today we'll zoom more in depth. Okay, in fact, whenever current flows into any current carrying conductor, any wires, there will be a magnetic field around it, not only for solenoid. Okay, so these are the learning outcomes. We will learn to draw the patterns of the magnetic field due to current in straight wires, as well as in solenoids, and then state the effect of the magnetic field by either changing the direction or the magnitude of the current. Okay, so how do we do that? We use it mainly by right-hand grip rule. And then we are also going to describe the applications of some of the magnetic effect of currents in electromagnets. Okay, in a lot of household appliances or daily appliances that you see, there is actually electromagnets in them. So we will discover how electromagnet works in these items. Okay, so there is this guy called Hans Christian Oersted. Okay, he was the one who discovered that electricity and magnetism is actually linked. So what he did was he carried out an experiment whereby he has a wire connected to a battery source and he put compass around it. Okay, the compass is to determine the magnetic field around the wire. So when the switch is open, no current is flowing. He observed that all the compass needle points to the earth north. Okay, because a freely suspended magnet will always point in the north-south direction. So all the compass needle points to the north. Okay, he placed one magnet below the wire and one compass below the wire and one compass above the wire. And both of them just points to the earth north, indicating that there is no magnetic field around this wire. Okay, but what happens when he closed the switch? He realized something. He saw that the compass needle actually deflects and it deflects in opposite direction. Okay, so the compass needle below the wire deflects to the left, while the compass needle above the wire deflects to the right. Okay, this when a compass deflects, it actually shows that there is a magnetic field around it. So he comes to this conclusion that a current carrying conductor actually produces a magnetic field around it. So the current carrying conductor is this wire. Okay, this wire is carrying current and there is a magnetic field around it, which can be shown by the deflection of the compass needle. Okay, so this is what he sees when there is no current. All the compass needle points in the same direction. And where there's current, you will see that the compass needle actually points in a closed loop circle. Okay, like that. Okay, it doesn't point to the earth north anymore. So there's a magnetic field, and this magnetic field in this case is in the clockwise direction. Okay, so he suggests that the magnetic field produced are actually like cylindrical shaped circle around the conductor itself. Okay, so you can see from here, okay, when the current is going up, you can see that the magnetic field formed by the compass needle is going in the anti-clockwise direction. Okay, so he comes up with this thing called the right hand grip rule to determine the magnetic field. So you have learned about right hand grip rule in the previous part about magnetism. You use it in a solenoid where current is flowing through the solenoid, and then you use the thumb to determine the north pole, which is the magnetic field. Okay, but right hand grip rule is actually very versatile. You can represent the current using fingers, where the fingers curl in the form of a solenoid. So when current is flowing through a solenoid, you use the fingers to represent the current because the current flow in coils and your finger can coil. Okay, so when a finger represents the current in a solenoid, the thumb represents the magnetic field, the north pole. But in this case of a straight wire, you can't use your fingers because your fingers will curl. So we don't use fingers, we will just alternate. If we were to use our thumb as the direction of the current flow, okay, so in this case, you can see that the current is going upwards. Okay, so I just point my thumb upwards in the direction of the current flow. Okay, based on my fingers curling, my fingers will be curling anti-clockwise. Okay, that's why I have a magnetic field in the anti-clockwise direction as this. Okay, you can scan the QR code to play around with how does the magnetic field looks like in the various different conductors. Okay, so next. Okay, then I'm going to introduce to you two different directions because in this chapter we will be looking at a lot of 3D diagrams. Okay, other than the four usual directions that can be represented easily on paper, which is up, down, left, and right. Okay, there is something called into the paper, or if you're looking at my screen, it means into the screen and out of the screen or out of the paper. Okay, so how do I remember it? Okay, they are represented by a dot and a cross. Okay, this dot and cross are just direction representation. Just like when you want to represent up, you draw a straight arrow up. So this dot and cross are just direction. It doesn't mean current, it doesn't mean magnetic field. It can be either current, it can be magnetic field, or it can even be a force. Okay, so it can be anything. It just represents direction. Okay, so a dot usually represents that the direction is going out of the paper. Okay, why is it a dot? I always think of it as an arrow. Okay, if the arrow is shooting out of the paper, what you see is the sharp tip of the arrow pointing towards you. So you see a dot. Okay, and then if it's a cross, okay, it simply means that you are looking at the backside of the arrow. Okay, so the arrow is actually going into the paper. So you see the back side of the arrow, which is a cross. Okay, so over here, I have wires that is carrying current into and out of the paper. Okay, so the first one, I have current. I see the sharp tip means the current is coming out of the paper towards me. Okay, so if I were to point my thumb towards myself using my right hand grip rule, I will get that the magnetic field is in the anti-clockwise directions. What happens when I reverse the direction of the current? Now I change such that my current is flowing into the paper. I see the back side of the arrow. So I have a cross here. Okay, so this pink color dot and cross in this scenario, only in this scenario, okay, they label this as the wire. It means that the current is going into and out of the paper. Okay, but sometimes this dot and cross can represent magnetic field or can represent force. But in this case, because it's the wire, it's the current in the wire. Okay, so this one is going into the paper. I see the backside. If I point my thumb into my screen, okay, I get that the magnetic field around it is in a clockwise direction. Okay, so you observe that the direction of the magnetic field reverse whenever the direction of the current reverse. Okay, so right hand grip rule is when there's only two things. When there's a current, there's a magnetic field. I want to determine the current or I want to determine the magnetic field, I use my right hand grip rule. Okay, next. Okay, you can take a look at this picture. This picture, both of them have the current coming out of the paper. I see the arrow key out of the paper. So both of them have their magnetic field in the anti-clockwise direction by the right-hand grid rule. Okay, but what can I conclude from these two magnetic field diagrams is that the magnetic field for I2 is closer compared to the magnetic field of I1. When the magnetic field lines are closer, it simply means that the magnetic field strength is stronger. So how is it possible that I have a stronger magnetic field here? It simply means that the current here is larger than the current here. So the strength of the magnetic field increases when the current increases. Okay, so over here I have two diagrams. You may, and these are compass needle placed around it. So there is actually a current flowing through this center wire. You need to determine the direction of the current flow. You may pause the video here to think about the answers. Okay, I'm going to go through the answers. The first one where it's going, magnetic field is going in the clockwise direction, is the current going into the paper. So I see the back side of the arrow, it's a cross. Okay, I put my thumb into my screen, I will see that it's clockwise direction. And obviously, the one where the compass needle all points in the opposite direction will be the current going out of the paper, the dot. Okay, so the next thing, other than straight wires, as long as current flows in any types of wires, so now we are moving into solenoid, there will be a magnetic field around it. So a solenoid is just a long piece of wire coiled around, okay, in a coil. Okay, and then over here, okay, you can see that this is an empty solenoid, while this is a solenoid wrapped around a soft iron core. Just take note that with or without the iron core, there will always be magnetic field. As long as got current flowing through it, there will be a magnetic field around it. Okay, so this one is covered in the previous chapter. You just curl your finger in the direction of the solenoid. Okay, you need to trace the direction of the current flow in front. Okay, I don't care about the one at the back. I just care about the front one. Okay, so in this case, the current is all going upwards. I curl my fingers such that I can see my fingernails and my fingernails are pointing upwards. I have my thumb, which points to the North Pole. Okay, so how can I increase the strength of this magnetic field? I can do the following: increase the current, increase the number of turns per unit length of the solenoid, or I can place a soft iron core within the solenoid, because magnetic field love to go through soft iron. Okay, love to go through magnetic material. So with a soft iron core, I will be able to concentrate all my magnetic field lines to the center. So this center portion will be a super strong electromagnet. Okay, you may pause the video here to think about the answers to the following. I'm going to go through the answers now. Given the direction of the current flow, I want you to determine the magnetic field and draw the magnetic field lines. So in the first case, is a solenoid. I have already drawn for you. The current flow is going up in the front solenoid. So if you were to use your right-hand grid rule and point, okay, it will be like this. Okay, you get a North Pole over at one end and South Pole over at the other end. Okay, and then you know your magnetic field lines. You are supposed to draw your magnetic field lines. Outside of the solenoid is always away from north towards south. Okay, so it'll be like this, away from north towards south. Okay, just take note that inside the solenoid, the field lines actually continues. Okay, you don't draw this out from North Pole to South Pole. Inside, it must still continue. Okay, it's a closed loop. So inside the solenoid is actually from south to north. Okay, next one. I have this diagram. Okay, this one is current coming out, and this one is current going into the paper. Okay, so if you were to draw, it's actually a solenoid current coming out and into the paper. Okay, so now all the arrows are going downwards. If I were you to use my right hand grid rule, it will look something like this. I must still again see my fingernails. My fingernails might be pointing down. I get my North Pole on the other end. Okay, over here and my South Pole here, and then I were to draw my magnetic field lines. It's again away from the north towards the south. Okay, so it'll be like this. Okay, next one. Okay, the next one, the magnetic field lines is given to you. So these are the magnetic field lines. Okay, and this circle, okay, are the magnetic field lines. You are supposed to determine the current flowing. Okay, so the first one is very straightforward. Okay, the first one, based on the magnetic field lines, it must go away from the north towards the south. So the first step, I should be able to identify that this side is the North Pole because it's going away from it, and this side is the South Pole towards it. Okay, and then I'm going to use my right hand grip rule to determine the direction of my current. Okay, so I will point my thumb downwards like a bullseye. Okay, and then I must be able to see my fingernails. I will see that my fingernails are actually going to the left. Okay, so my current, okay, so it looks like this. Okay, so my current is actually going to the left in the front solenoid. Okay, and next one, in order to form this clockwise direction, my current must be going into the paper. Okay, so I see the arrow tail. Okay, next question. A current in a solenoid creates a magnetic field. What is the effect of the magnetic field at point P using a smaller current and in the opposite direction? So I have a compass here. So what will happen to this compass when I use a smaller current? Okay, so when I use a smaller current through this solenoid, my magnetic field strength would decrease. Okay, so it's either A or C. And if my current reverse, if I were to reverse the direction of my current, my magnetic field will also reverse. Okay, so answer is actually A. Okay, okay, next. I have a solenoid over here. I have a current passing through this solenoid. And there is a compass over here. What will happen to this compass when current starts to flow in this solenoid? Okay, so the first step, always trace the direction of current flow. So the current will all be flowing upwards. Then use my right hand grip rule. Okay, I will have my thumb pointing at P. So P will be a north pole, Q will be a south pole. And if my compass needle is placed here, I know that it should always point towards the south because the compass needle represents the magnetic field line. Okay, so the answer should be C. Okay, so summary, whenever a current flows in a wire, a magnetic field will be produced. The direction of magnetic field can be determined by using the right hand grip rule. Okay. Okay, I will stop here for the first part. In the second part of the video, then we will go through some of the uses of electromagnets.